Yeah, I think the key thing, Robert, is the TDP of this part is still 105 watts, right?
That's right.
So
That's right.
there's some give and take that has to happen in order for us to fit within that envelope. And it is still overclockable, right?
Is unlocked. Yeah. Is it? And it's just and I think that is a good point to make. Is
Hello and welcome back. In today's video, we're overclocking the AMD Ryzen 7 5800X3D CPU all the way up to 4741 MHz using the ASUS ROG Crosshair VIII Extreme motherboard and EK Quantum custom loop water cooling. Obviously, this CPU is not meant to be overclocked as it is supposed to be locked for overclocking. However, there's always a couple of tricks that we can use to try and find more performance in our system. I found that the voltage suspension feature available on the Crosshair VIII Extreme motherboard was particularly useful for this overclock. As I said, the normal overclocking tools are not at our disposal, so it will be a shorter video, but I hope you enjoy it nonetheless. The AMD Ryzen 7 5800X3D is part of AMD's Zen 3 Ryzen 5000 processor lineup. The original 4 Zen 3 Vermeer desktop CPUs launched at the end of 2020. Since then, the product line has expanded to 10 SKUs ranging from the 6-core Ryzen 5 5500 to the Ryzen 9 5950X. The Ryzen 7 5800X3D is the odd one out in the bunch, as it's the only processor that features the 3D V-Cache technology. I won't cover the ins and outs of 3D V-Cache in this video, as plenty of other media and channels already did a much better job than I would do. The long story short is that AMD put an additional L3 cache on top of the single CCD on the 5800X3D package. That effectively triples the on-package L3 cache from 32 MB to 96 MB, and it is supposed to offer improved gaming performance. The Ryzen 7 5800X3D is the only consumer processor with the 3D V-Cache technology. The CPU has 8 cores with 16 threads, a base frequency of 3.4 GHz, and a maximum listed boost frequency of 4.5 GHz. In comparison, the Ryzen 7 5800X also has 8 cores with 16 threads, but has a base frequency of 3.8 GHz and a maximum boost frequency of 4.7 GHz. The TDP for both chips is 105 watt. A slight difference between the 5800X and the 5800X3D is that the latter is the B2 stepping. We already talked about this minor difference in SkatterBencher number 29, where we overclocked a Ryzen 9 5900 B2. While there's been a lot of speculation about the difference between B0 and B2 stepping, the only significant difference is readiness for 3D V-Cache. In this video, we will cover only 2 overclocking strategies. First, we increase the fabric clock and memory frequency. Second, we overclock using reference clock and voltage suspension. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this video guide. Along with the AMD Ryzen 7 5800X3D processor and ASUS ROG Crosshair VIII Extreme motherboard, in this guide, we will be using a pair of G.Skill Trident Z DDR4 4266 memory sticks, an ASUS ROG Strix RTX 2080 Ti graphics card, a 512GB M.2 NVMe SSD, a Seasonic Prime 850 Platinum power supply, the Elmo Labs EasyFan controller, the Elmo Labs power measurement device, the Elmo Labs EVC2SX, the EK Quantum magnitude water block, and EK Quantum water cooling. All this is mounted on top of our favorite Open Bench Table V2. The cost of the components should be around $4,200. I already explained how I use the Elmo Labs products in SkatterBencher number 34. By connecting the EFC and PMD to the EVC2 device, I monitor the ambient temperature, water temperature, fan duty cycle, and CPU input power. I include the measurements in my Prime 95 stability test results. I also use the Elmo Labs EFC to map the radiator fan curve to the water temperature. Without going into too many details, I've attached an external temperature sensor from the water in the loop to the EFC. Then I use the low-high setting to map the fan curve from 25 to 40 degrees water temperature. I use this configuration for all overclocking strategies. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start any overclocking, we should first check the performance at default settings. Please note that, as I mentioned before, the 5800X3D has none of the overclocking features available. That includes both manual overclocking as well as overclocking through Precision Boost Overdrive. However, Precision Boost, the boosting algorithm, is still present. These are the default settings for the PB algorithm. These values are very similar to the typical values of any Ryzen 5000 series CPU, except for the VID. On other Ryzen 5000 CPUs, the maximum allowed VID is 1.5 volt, but the 5800X3D is limited to only 1.3 volt. According to AMD, that's to protect the 3D V-cache as it's more sensitive to voltage.
So I think on the desktop parts, you've seen us ship parts that range up to 145 or even 1.5 volts in boost, and that is not the limit for the 3D V-cache technology. The voltage limit on that is more like 1.3 to 1.35.
Here is the benchmark performance at stock. Here are the 3D Mark CPU profile scores at stock. When running Prime 95 small FFTs with AVX enabled, the average CPU effective clock is 4054 MHz with 1.184 volts. The average CPU temperature is 90.3 degrees Celsius. The ambient and water temperature is 22.3 and 30 degrees Celsius. The average CPU package power is 115.8 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4190 MHz with 1.221 volts. The average CPU temperature is 83.9 degrees Celsius. The ambient and water temperature is 22.2 and 30 degrees Celsius. The average CPU package power is 114.8 watts. Now let us try our first overclocking strategy. But before that, make sure to locate any of these three following buttons: Save Boot button, Retry button, and CMOS Clear button. In our first overclocking strategy, we make use of fabric overclocking as well as ASUS DOCP. DOCP stands for Direct Overclock Profile, and it is an ASUS technology that aims to replicate the Intel XMP that we know from Intel platforms. XMP allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. If the motherboard supports XMP, you can enable higher performance with a single BIOS setting. So it saves you from lots of manual configuration. The fabric connects the CPU cores with the on-package I/O die, which houses the memory controllers. When the CPU cores want to store or retrieve data from the system memory, they do this via the Infinity fabric and the memory controllers on the on-package IOD chip. By default, the memory, fabric, and memory controllers are running in synchronous mode. That means they all operate at the same frequency. When overclocking the system memory, you can use either synchronous mode or asynchronous mode. In asynchronous mode, the memory controller will operate at half the system memory frequency, and the fabric clock will also run below the system memory frequency. That will result in a performance penalty. The performance penalty is application specific, as sufficiently high memory frequency may overcome that performance penalty. While our memory kit is rated at DDR4 4266, I will run it at DDR4 3800. That's because I want to run the fabric, memory, and memory controller in synchronous mode. While the fabric was able to overclock all the way up to 2133 MHz, there were a lot of Windows hardware errors. So I could only get it stable up to 1900 MHz, and that's what I will run it at in synchronous mode. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to DOCP Standard. Set memory frequency to DDR4 3800 MHz. Set F clock frequency to 1900 MHz. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. We see only performance improvements in specific memory-sensitive benchmarks, but little to no improvements otherwise. The maximum performance improvement is plus 8.89% in AI benchmark. When running Prime 95 small FFTs with AVX enabled, The average CPU effective clock is 4035 MHz with 1.181 volts. The average CPU temperature is 90.3 degrees Celsius. The ambient and water temperature is 22.5 and 31 degrees Celsius. The average CPU package power is 129.1 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4247 MHz with 1.232 volts. The average CPU temperature is 87.5 degrees Celsius. The ambient and water temperature is 22.5 and 30.4 degrees Celsius. And the average CPU package power is 118.8 watts. In our second overclocking strategy, we will make use of reference clock overclocking and voltage suspension to overclock the 5800X3D processor. In SkatterBencher number 29, I refer to this approach as Shimino charging precision boost overdrive. But since we don't have access to any of the PBO tools, I guess we're just Shimino charging precision boost. Anyway, let's first have a look at a couple of challenges that we're facing with this 5800X3D. Let's figure out the things that are potentially going to hold back our mission to get more performance. Frequency. If we were able to increase the operating frequency with PBO tools like Fmax Override and Curve Optimizer, we'd be getting higher performance. Temperature. As we can see from the Prime 95 results, we reach TJ max at 90 degrees Celsius even when using custom loop water cooling. Voltage. As I highlighted earlier, the maximum allowed voltage is only 1.3 volt. That will limit our overclocking potential. Effective clock. We can also see from our Prime 95 results that the CPU effective clock is noticeably lower than the CPU core clock. Finding a way to increase the effective clock to match the core clock will also help performance. We will address that first challenge with reference clock overclocking and the 3 other challenges with voltage suspension. However, before we get going, let's first have a quick refresher on how Precision Boost 2 works. Every core inside your Ryzen CPU has a factory-fused voltage frequency curve. This curve describes the relationship between an operating frequency and the operating voltage that is required to run that frequency stably. AMD Precision Boost technology uses this VF curve information to dynamically increase the CPU operating frequency beyond the base clock frequency. The boosting algorithm first determines the maximum allowed voltage for a given set of input parameters. The inputs include power, current, and temperature, but also quantity of active cores, the core's quality, and so on. Once the algorithm has determined the maximum allowed voltage, it applies the associated frequency based on the VF curve. While there's no detailed information available on how the algorithm works precisely, what we do know is that, generally speaking, if there's more thermal, current, and power headroom, your CPU will boost to higher frequencies. The Ryzen 7 5800X3D has 2 chips on package, one CCD and one IOD. CCD stands for Core Chiplet Die and is just a die on a Ryzen CPU with CPU cores. The Zen 3 CPU cores are packed together in a CCX or core complex. A Zen 3 CCX consists of 8 individual cores, each with its L1 and L2 cache and a shared L3 cache. A 100 MHz reference clock input drives the frequency of the CPU cores. Each CCX has its own PLL and thus can run an independent frequency. The cores within a CCX share the same PLL, so they'll run at the same frequency. The additional L3 cache also runs at the same frequency as the CPU cores. The reference clock is, well, the reference clock for many parts in your system, including the CPU cores, the fabric, memory controllers, the system memory, PCIe, SATA, and so on. When increasing the reference clock frequency, you change all the frequencies associated with that reference clock. While this can result in additional performance, it can also cause instability, so be careful. Particularly relevant for this platform is that I need to use an M.2 drive that is connected directly to the CPU PCIe lanes if I want to use over 101 MHz BCLK. And that works all the way up to 104.2 MHz. Beyond that reference clock, I need to use a separate add-in card with a SATA controller that has an independent clocking circuit. As the precision boost algorithm is ref clock unaware, we can use this reference frequency to push the CPU frequency higher than what the algorithm wants to set it at. For example, let's say the algorithm finds sufficient voltage headroom for 1.3 volt, and that voltage is associated with the 45x ratio. Using a base clock frequency of 101 MHz instead of the default 100 MHz, the actual frequency at our 1.3 volt voltage point will be 4500 times 1.01 equals 4545 MHz. I use a reference clock frequency of 104.2 MHz in this specific case. Combined with the AMD default maximum boost frequency of 4550 MHz, this results in a new maximum boost frequency of 4741 MHz. While that should offer a nice boost in performance, this won't be stable without tuning the operating voltage. The VDD-CR CPU voltage rail provides the voltage to the Vermeer Zen 3 cores. This voltage rail is shared across the entire CCD, so each CPU core and the L3 cache will be provided with the same voltage. An external voltage controller will then power the VDD-CR CPU voltage rail. There are two ways to control that voltage. One through precision boost algorithm, so automatically, and one with manual voltage input. Since we're trying to overclock using precision boost, let's just focus on that one. When the precision boost algorithm determines the optimal voltage for a given situation, it will request the voltage controller on the motherboard to provide that voltage. It does this with a VID request. The voltage controller takes that VID request, offsets this value with any configured voltage offset, then outputs this voltage back to the CPU. The actual CPU core voltage is still subject to any impact from the VRM load line. When we're overclocking our Ryzen CPU using reference clock with precision boost enabled, we're making the CPU run at a higher frequency for a given voltage. Without voltage adjustments, that won't be stable. One available approach on most, if not all, AM4 motherboards is using a static voltage offset. The voltage offset applies across the entire VF curve. We can improve stability at the highest frequency range by adding a voltage offset. But keep in mind that adding an offset to the whole VF curve also means getting higher voltage at lower frequencies. So, in heavy multi-threaded workloads, you'll run out of thermal headroom faster than without the voltage offset. While a static voltage offset will definitely help us to see the highest possible frequencies, for a daily driver we need a dynamic voltage that changes based on the conditions that the system is in. And this is where voltage suspension comes in handy. Voltage suspension is a feature that was first available on the ROG Crosshair VIII Extreme motherboard and is now also available on select ROG Z690 motherboards. I covered the feature extensively in SkatterBencher number 29, so feel free to check out that video if you want to have a really detailed understanding of how the feature works. For this video, I'll try to keep it as short as possible. In essence, the purpose of voltage suspension is to force the core voltage to stay within a specific range, even when using a dynamic voltage like with precision boost overdrive. There's a unique hardware circuitry on the motherboard PCB to achieve just that. Essentially, the circuitry has two main functions. One function is to monitor the CPU VID voltage requests, and another function is to adjust this request with our custom voltage suspension rules. As a quick reminder, here's how the voltage is set on your AMD Ryzen CPU when precision boost is enabled. First, the algorithm evaluates the current CPU conditions and determines the optimal voltage. Then, the CPU sends the voltage request using a VID to the voltage controller. The voltage controller will take the voltage request and add any positive or negative voltage offset. This adjusted voltage is then sent back to the CPU, but may be impacted by the VRM load line. The CPU will also sense the incoming voltage and adjust the VID voltage request if the sensed voltage is significantly lower than the requested voltage. The voltage suspension adjustment happens after the voltage controller adjusts the VID voltage request with the offset. We can configure the voltage suspension by setting the voltage ceiling and floor. The former is our maximum voltage, while the latter is our minimum voltage. We can configure it either in static or dynamic mode. In static mode, we set a maximum and minimum voltage, and the voltage suspension function will try to keep the voltage between these two levels. In dynamic mode, we make our own voltage frequency curve, though we don't use frequency as a parameter. Instead, we configure the ceiling and floor voltage as a function of our 4 points defined by a voltage and temperature, so it's more like a voltage temperature curve. I won't get into the nitty-gritty details of how to configure voltage suspension, just check out SkatterBencher number 29 to learn about that, but I can explain the purpose of my settings. Here are my voltage suspension settings. When the processor is relatively cold, 65 degrees Celsius or lower, my configuration will force the CPU voltage between 1.325 volt and 1.375 volt. That's slightly higher than the AMD voltage limit of 1.3 volt and offers stability at the increased maximum boost frequency of 4741 MHz. When the processor is relatively hot, 85 degrees Celsius or higher, my configuration will force the CPU voltage between 1.1625 volt and 1.2 volt. That's slightly lower than the 1.18 volt we see in Prime 95 with AVX and 1.23 volt in Prime 95 without AVX from our previous overclocking strategy. Not only does this help us achieve lower operating temperatures under full load, but as a consequence, we also see 150 to 200 MHz higher all-core effective clock frequencies. A major downside of voltage suspension is that it's a reactive mechanism that responds relatively slowly to changing conditions. So while it is excellent at managing the voltage over an extended period of time, it is not that good at managing the voltage over a short period of time. The Precision Boost algorithm updates its target frequency many times per second to ensure the optimal performance is reached at any given time. Especially in rapidly changing conditions where the CPU goes from full load to idle to single core load, the voltage suspension can be slow to react. There are two extreme scenarios we need to keep an eye out for. First, when the CPU goes from a light load to full load. Here, initially, the temperature will be relatively low, and thus the voltage suspension has the voltage set high. This high voltage may still be applied when the cores are at full load. The high voltage may cause excess temperature. Second, when the CPU goes from full load to light load. Here, initially, the temperature will be relatively high, and thus the voltage suspension has the voltage set low. This low voltage may still be initially applied when a single core is in light load. The low voltage may cause instability. We cannot do much to address the first scenario other than letting the Precision Boost algorithm automatically adjust the frequency and VID requests. For the second scenario, we can add a manual positive voltage offset. That will help retain stability in the initial stages of the Precision Boost algorithm, boosting to a high frequency. The appropriate voltage offset depends on how much you've pushed up the Precision Boost frequency by overclocking the reference clock. In our case, we set a voltage offset of plus 50 mV. Before going into the BIOS, you need to know a couple of settings when using reference clock overclocking with the Crosshair VIII Extreme motherboard. The motherboard is tuned for both ambient and extreme overclocking and thus has a lot of auto rules implemented to help with easy overclocking. When using reference clock overclocking, the auto rules of the BIOS force the CPU into OC mode and thus has the Precision Boost algorithm disabled. So you'll end up with a fixed ratio in the operating system. To avoid this, enable both Core Performance Boost and Force OC mode disabled. Also, make sure to enable Global C-State Control. Without it, the effective clock frequency will increase until 101 MHz reference clock, but then sharply drop by 100 MHz. You ensure that the Precision Boost frequency keeps scaling with the reference clock by enabling this setting. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to DOCP Standard. Set BCLK frequency to 104.20. Set memory frequency to DDR3681 MHz. Set F-clock frequency to 1840 MHz. Set Core Performance Boost to Enabled. Enter the external DigiPlus Power Control submenu. Set Core Voltage Suspension to Enabled. Set CO Mitigator to 0.3. Set Voltage Floor Mode to Dynamic. Set Floor Low Vmin to 1.1625. Set floor hot temp to 85. Set floor high Vmin to 1.325. Set floor cold temp to 60. Set voltage ceiling mode to dynamic. Set ceiling low Vmax to 1.20. Set ceiling hot temp to 85. Set ceiling high Vmax to 1.375. Set ceiling cold temp to 65. Leave the external DigiPlus power control submenu. Enter the Tweaker's Paradise submenu. Set Force OC mode disabled to enabled. Leave the Tweaker's Paradise submenu. Set CPU core voltage to offset mode. Set offset mode sign to plus. Set CPU core voltage offset to 0.05. Go to the advanced menu. Enter the AMD CBS submenu. Enter the CPU common options submenu. Set global C state control to enabled. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. With a 4.2 increase in reference clock, we see about a 4% performance increase across the board with a peak performance improvement of 12.92% in AI benchmark. Overall, not too shabby for a CPU that AMD locked for overclocking. When running Prime 95 small FFTs with AVX enabled, the average CPU effective clock is 4214 MHz with 1.176 volts. The average CPU temperature is 93.4 degrees Celsius. The ambient and water temperature is 24.4 and 32.2 degrees Celsius. The average CPU package power is 125.6 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU effective clock is 4359 MHz with 1.208 volts. The average CPU temperature is 86.7 degrees Celsius. The ambient and water temperature is 24.4 and 31.6 degrees Celsius. The average CPU package power is 131.7 watts. As a side note, even with these elevated frequency and voltages, it doesn't appear we're near the PPT, TDC or EDC limits imposed onto the 5800X3D. So, in other words, these standard precision boost parameters are more than sufficient for this CPU as the primary limiter is operating temperature. Alright, let's wrap this up. The AMD Ryzen 7 5800X3D processor is the first and currently only consumer-grade CPU with 3D VCast technology. It is also a locked CPU, meaning that it can't be overclocked. That is an atypical deviation of AMD's usual approach to enthusiast products for the enthusiast market. Most of the time, their CPUs are overclockable. The argument that AMD gives is that the 3D V-cache is more sensitive to voltage and they want to prevent any users from doing any damage to the CPU through overvolting, essentially. While I understand this argument and this reasoning, I think they could have gone about it in a different way. With Precision Boost Overdrive, we're already very familiar that not all parameters can be unlocked to essentially an unlimited value. For example, temperature. We cannot adjust the TJ max above what AMD fuses at the factory at, right? So for most CPUs, it's about 95 degrees centigrade. The TJ max, we can't override that. Same with Fmax. We can't increase the Fmax above plus 200 megahertz. Same with VID. We can't change the VID to go over the 1.5 volt that is specified for most of the Ryzen 5000 CPUs. So AMD could have just imposed a VID limit to 1.3 volt rather than 1.5 volt. In addition to that, if your argument is that you are worried about the voltage for the 3D V-cache, then surely Curve Optimizer, the one tool that you advertise as, great for undervolting, would be the tool that you want to give those 5800X3D customers, right? Anyway, I had a lot of fun trying with reference clock and with voltage suspension to further overclock the CPU. With the reference clock, we can offset precision boost algorithm to essentially boost to slightly higher frequencies than what I would normally boost at. And with voltage suspension, we can find ways to trick the voltage to run either a little bit higher than what precision boost wants to set it at or a little bit lower than what precision boost wants to set it at. I got it all the way up to 106 megahertz BCLK, and that's about 4.8, slightly over 4.8 gigahertz on the CPU. but it wasn't quite stable. My stable setting was about 104 megahertz BCLK and 4.7 gigahertz Ryzen 5800 X3D CPU core frequency. The main limiting factor for the CPU seems to be sort of the frequency where I'm at. Like, I didn't really see any improvements with adding a lot more voltage, not even for single-threaded boost. So I think that's pretty much the maximum of this CPU. Anyway, that's all for today. I thank you very much for watching. I hope you found this overclocking journey as interesting as I found it. I want to thank my Patreon supporters, Coffee Penbit and Andrew, for supporting my work. As per usual, if you have any questions, feel free to drop them in the comment section below. I'll also put up a written version of this video on my blog if you want to review the settings or the performance gains. And that's it. See you next time.